Okay, I want to just welcome everybody to today's webinar. This is Innovation Insights. It's our monthly webinar series with three separate speakers, all with, with great technologies that we think that may not be as fully appreciated as people understand. But again, another great lineup for this month. What it is our monthly website. IACMI industry members and R&D partners. So we'll typically try to target one small company, one large company, one research partner, which is the university or national laboratory. And then if you are an IACMI member and you'd like to present, just get a hold of me and we'll get you on the schedule. So just a reminder about IACMI, 3 C's of convene, connect, and catalyze. We want to bring people together. We want to make sure they get connected to each other, and then we want to catalyze innovations in research and commercialization, through a whole bunch of various methods to do that. Now, as you can see, some of the things, we have the IACMI Consortium. We've achieved our DOE goals in terms of cost, energy, and recycling to date. A lot of work, as you can see, in materials, in modeling and simulation, and of course in talent development. We're looking forward to this. Our members meeting is coming up October 5th through the 7th, and getting back together as large groups for that members meeting. So we certainly invite you to come to that. So our presenters today, we have 3. We have Rick Neff, who's a consultant and a consultant to THERMWOOD. He's going to be presenting on the LSAM, the large scale additive manufacturing process that THERMWOOD has. Rick is formerly with Cincinnati Incorporated, so was very involved in the original development of the BAM in conjunction with Oak Ridge National Lab. So he's going to spend some time talking to us about the LSAM and its application to tooling. Vern Benson, I've known Vern for many years, back when he worked for Hercules Aerospace. He hasn't left yet, although the name of the company has changed several times since. Vern's a technical fellow in composites automation, and he'll talk to us about automated stiffener forming, which is flying today on the A350. So that's a very exciting technology. And then finally, Professor Penumadu from University of Tennessee, Knoxville, will give us some insights into using fiber optic sensing and remote sensing technologies for measuring loads and strains on composite bridges and in other applications. So Rick, I'm going to turn it over to you, and you can share your screen with us and bring us forward.
Great. Sounds great, Dale. Thank you.
Thank you.
Let's see if I can get this all working right here. All right, there we go. So thanks for inviting me to be part of IACMI's Innovation Insights. It's a very exciting group of webinars, and hope to live up to your expectations today. Presentations on large-scale additive manufacturing. As Dale said, I'm a consultant and have been working for THERMWOOD to help them with their representation to IACMI, actually. And so we're going to talk about additive manufacturing, and some people are like, well, what's that? Well, it's very similar to a term that we may be more familiar with, 3D printing, but additive manufacturing actually encompasses more than just the printing of the part. It includes design for additive manufacturing, the CAM process or slicing, print optimization, 3D printing, and post-processing. And there are 7 forms of additive technologies according to ANSI, but I think there's more like 14 if you really start looking at them, but we're really only going to talk about one today, and that's material extrusion. And the extrusion process was really first developed by a guy by the name of Scott Crump in 1988, 33 years ago. And Scott's company is Stratasys, one of the largest companies in additive manufacturing, and they call the extrusion process FDM, or fused deposition modeling. A more generic term is fused filament fabrication. And for large scale, BAM and LSAM have been trademarked by various companies, LSAM being the THERMWOOD large scale additive manufacturing system. The way extrusion systems work is they start with plastic. The small systems start with a filament that looks like this. The filament is then pushed through a heated tube called a liquefier by a gear drive, where it's melted and extruded out in a little bead where you can build up a part layer by layer, sort of like hot glue coming out of a hot glue gun. Now imagine this really large scale, and that's what the LSAM is. And instead of using filament, we use plastic beads like you'd use for injection molding. And they're pre-compounded with carbon fiber, short carbon fiber, or sometimes glass fiber. The pellets need to be dried before they're processed. So they're drawn up with a vacuum into a commercial dryer, and then they're extruded in large beads by the system. Now, what's interesting about THERMWOOD is that they have an optimized extruder for large scale additive that has two melt cores. One is 40 millimeters, another is 60 millimeters. The 40 millimeter can put out 200 pounds per hour, and the 60 millimeter is 500 pounds per hour. The little desktop machines aren't near a pound per hour, so this is very much larger. And what's different about this is that most of the other extruders that are used in the plastics industry use friction to add heat to the plastic as it's being melted. Whereas this really uses the screw as a conveyor and adds almost all the heat with heating jackets on the outside. Very interesting, and it makes for a very consistent process. Another thing that's interesting about it is that it was originally designed so that it was easy to swap melt cores. If you have a really large high temperature application, you can use a larger melt core. And then you can simply slide the servo motor up, disconnect the electrical and mechanical connections, pull out the melt core, and put in the other size melt core. Another unique feature is that the THERMWOOD system has something called a melt pump. And what the melt pump does is it exactly meters out the right amount of material so that you wind up getting a bead that's very accurate. The bead happens to be 5 millimeters tall and 12 millimeters wide, and it varies by very little, so that when you're creating a tool, you can exactly fill it up. You can make it with almost no voids in it. Now, when you lay down material just coming out of a nozzle, what you find out is that the strength of the bead is very strong along the bead because the fibers all line up that direction. But the layer-to-layer bonding isn't all that good. The strength, if you pull it in the Z direction, is not too strong. Now, Oak Ridge had a partial solution to that by using a tamper that tamped the material down and improved the layer-to-layer bonding by a considerable amount. But what we see today is that the leading technology is a temperature-controlled compression wheel that THERMWOOD employs. And that really improves the layer-to-layer bonding to the point where you're very close to the strength of the thermoplastic material itself without the fibers in it. So at Oak Ridge, they discovered this property that they call the Goldilocks effect. If the part's too hot, you find that when you print on top of it, the material can't support the weight of the material on top, and it kind of slumps down or droops. If it's too cold, the materials don't bond well together. A little further investigation into that, and THERMWOOD has developed what they call the continuous cooling process. So what happens is that when you put a layer down, when you use a really large layer like THERMWOOD does, when it starts to cool, it cools along the outside edge and along the top to where it cools enough that it could support a new layer on top. When the new layer comes along and is deposited, what happens is it's hot enough that when it's forced into the layer below it, the material melts through to the molten core of the lower layer, and the two layers are bonded together very effectively. Another thing that's really interesting is something called vertical layer print, or VLP. And with the continuous cooling process, you don't actually have to print horizontally, you can print vertically. And that's a really good option for making tools. This is a tool here that's being printed on a vertical wall on a beadboard. And you can see that in this time lapse, the wall keeps moving backward from the print head. The very area where it's being printed isn't supported at all. It's only supported once the wall moves back over the table. And you can get some really nice shapes out of this. What this allows you to do is have the printing go in the proper orientation so that when you machine the tooling surface, you wind up without any voids or gaps like you might see if you had a start stop in the plastic, or if you were only building the layers horizontally here. Another thing that's important is making sure we do have the right temperature. And early on, Oak Ridge did some really good infrared thermal analysis of the project. And THERMWOOD has taken it to another level with an IR camera on their machine so that they're continually monitoring the process. But then just this year, THERMWOOD announced a really new thing called thermal sensor layer automation. And what this is they use a small thermal sensor that is right in front of the nozzle as it's depositing material. So it's looking right at the substrate at the instant before material is deposited on it. So you know exactly what temperature the substrate is before you put fresh material on. Since the deposition head rotates to have the wheel follow the deposition, you always are looking right in front of the nozzle. What's really cool about this is you can set up a material parameter library for the material that you're depositing so that you have parameters built in on how fast the layer needs to be and what you can do, what sort of methods you can use to slow down or speed up, whether you go to a minimum deposition speed, and then if you have to go slower than that, you stop between layers. This can all be programmed in. And what it makes for is it makes for a really easy process for 3D printing. A lot of the difficulty that was included in some of the earlier machines has been eliminated. So what materials can you use for tooling applications? Well, there really are 3 manufacturers that have worked with THERMWOOD to develop materials that are all qualified to run in different types of tooling applications. Tecmer PM, Sabic Innovative Plastics, and AirTech all have their own product lines and each have multiple materials for different applications, for different temperatures, depending on what you want to do. The first material that we were most excited about in the tooling world was PPS. And PPS is a high temperature material. It's semi-crystalline, and you could load it with up to 50% carbon fiber, meaning that it has a very low CTE. But one of the problems was that most printers could not print it to the point where it was dense enough that it would hold a vacuum. It needed to be sealed with a secondary operation. The THERMWOOD LSAM was the first one that could actually print this material without coatings that could hold a vacuum. Another interesting material is PSU, or polysulfone, with carbon fiber. That was first used in a collaboration between Purdue University, Applied Concepts Engineering, or ACE, and their parent company, Applied Concepts, and Tecmer PM. What they made is they made a drip pan for a Chinook helicopter. It was put in an autoclave at 275 degrees Fahrenheit, 90 degrees PSI, or 90 PSI, and came out with a really nice part. The feedback from that is that the traditional tool took $6,000 worth of material, while the additive manufacturing tool was less than $4,000. The labor hours were reduced from just over 69 to under 22 hours, and the lead time went from 8 days to 3 days by implementing additive manufacturing. By the way, they let this tool ride in the back of their autoclave for months so that it got through a lot of cycles, and it never degraded as far as we could tell. Another interesting material is polyethersulfone, or PESU, which is autoclavable at 350 degrees Fahrenheit, has vacuum integrity. And you can see a tool here that was developed along with Boeing and AFRL to test the capabilities of PESU. So what applications do we see? Well, transportation is one area. And there's a company called Local Motors that has an autonomous vehicle called Ollie that's deployed today, running passengers around, where they use an LSAM to print the frame. And this is what the frame looks like. as printed on THERMWOOD's LSAM in Tennessee, in Knoxville. But like Lonnie Love from Oak Ridge National Labs would say, there are three good applications for large scale printing, and that's tooling, tooling, and tooling. And so let's talk a little bit more about tooling. Boat molds are one area where there's been a lot of work done. This happens to be a Tahoe Boats T16 that was 3D printed in several pieces, bonded together, and then machined on an LSAM. It was then hand finished to a beautiful shiny finish. And this looks just like the boat. And why would you want something that looks like the boat that's not a boat? Well, because we use that to actually make the molds that are used for production. So this plug is used to have a fiberglass mold made on top of it with the structure that's needed added to it. And the thing is they don't need just one mold. They need many molds because it's a very high production boat. So they can only make about one boat a day per mold. So depending on the number of boats per day they need to make, they need more molds. So this is a good way to do it. This is another application for a boat mold. And what this is it shows something using a VLP process. So here it is when it's put together. And this is a time lapse of the printing. And then the interesting thing about the THERMWOOD is it has a machining head on it as well. Let's see, excuse me, I wanted to show you one other thing here. Nope, I was hoping to be able to jump through this video, but I can't jump through it like I could when I was not in presentation mode. So anyhow, we will jump over and I will talk about another boat mold. This is a 51-foot boat mold that has rockers built into it. So the concept is here you can lay up one half of the boat and then you can roll it over on the other side and lay up the other half. This shows the LSAM MT or moving table system printing one of the sections for this tool. And you'll notice that the printing looks like it's very slow. This is about as slow as we can run the LSAM. And the reason why it's so slow is because there's not a lot of material in each layer. So we have to give it plenty of time to cool down before we put the next layer on top. And when we take these pieces and start to stack them up, this is what the mold looks like. So in aerospace, there's some cool applications too. This shows a helicopter blade mold being printed at actual speed for Bell Helicopter. And Bell now has an LSAM installed in their development center in Fort Worth. Pretty exciting project. But once the tool was printed, it was moved over on its side, machined on the top there, and then mounted to a steel frame so it could easily be rolled in and out of the autoclave. Another interesting application is trim tools. When you take a composite part off the main tool, you then need to trim the outside edge, maybe drill some holes in it. And to do that, you need a fixture that can hold it very precisely in space. So we call that a trim tool. And this is one that was done for General Atomics. And you can see that it was printed in two pieces. And the reason for that is you can print almost twice as fast because we can easily print two pieces in the proper amount of time for a single layer. So we print the entire part in about 16 hours. We can bond the two layers together. You see here on the thermal monitor where it's white is the very hot material that's just been deposited. Green is the proper temperature to print on, and the lower layers, which are red and pink and blue, are too cool to print on. So we know that we were printing on green, which is the right temperature. So the machining for this part actually took about 32 hours. So about twice as much machining time as the printing time. This is another trim tool, one that was made in cooperation with Boeing, and it was made using a VLP process. So it was printed with vertical layer print and then machined. Some other interesting things are architecture, and there have been a bunch of great applications, but one I want to show you is the Al Davis Memorial Torch that's in Allegiant Stadium in Las Vegas, which we think might be the world's largest 3D printed structure.
This is the rendering we were shown. Over the course of 2 years, this is what we built. But transferring that idea on paper into the world's largest 3D printed structure that's also clad in more than 18,000 pounds of precision machined aerospace grade aluminum and is a stunning visual anchor for Allegiant Stadium in Las Vegas had a few challenges. We love doing what's never been done before. And we knew right away that for a project of this size and shape, traditional building methods just wouldn't work. After months of research, we found the solution, and it was in Indiana. So that's where we went to purchase one of the world's largest 3D printers. At the time, only the third LSAM ever built by THERMWOOD. Since this is a brand new piece of technology applied to a task that had never been done before, ever, by anyone, we had a bit of a learning curve getting the machine to do what we wanted. But once we got it dialed in, we were printing 2 unique 350-pound blocks a day, and then machining each one to a tolerance of within plus or minus 5,000ths of an inch. Then we drove them down the street to a big warehouse where we checked fit, sanded for final finish, applied protective coatings, and made sure everything would go together perfectly on site. And they did. Using 23 cubic yards of material and standing 93 feet tall, this is the world's largest 3D printed structure by both volume and height. Guinness World Records pending. This thing is over 40 tons of carbon fiber composite alone. We stacked 226 huge blocks, 23 rows high, for a total of more than 5,000 layers of printed material. Too many numbers? Here's something easy to remember. Since the material is a mix of thermoplastic and carbon fiber, it's really strong. This whole structure is freestanding. There's a metal frame inside, but it doesn't provide structural support. It's just there so we can get to the top. After some experimentation with vinyl and paint, it was decided that the only way to make the torch look like it's clad in real metal is to use, well, real metal. We already had our hands full printing and machining composite parts, so we partnered with Ultratech Aerospace in Kansas City to cut over 1,000 unique aerospace-grade aluminum panels. These folks are pros at creating incredibly precise shapes, which is important. Everything needs to fit together perfectly. But we also needed a consistent jewelry finish on every part, and we checked them with a microscope. All 1,143 unique panels with a microscope. Then we gave every part a protective and uniform ceramic coating with a robot that we engineered and programmed specifically for the task. We are DI, and we are proud to have created the world's largest 3D printed structure, the Al Davis Memorial Torch at Allegiant Stadium in Las Vegas, Nevada.
So Dimensional Innovations is doing some really cool stuff on their LSAM. And the first one, the LSAM was a 1020, a 10-foot wide by 20-foot long and 5-foot tall build platform. The next one was 1040, which is the same thing, only 40 feet long. And then the LSAM MT to try and drive some of the cost out. The milling head and deposition head were put on a single bridge with a moving table under it. Then some customers wanted some guarding, so took that same concept and put it on a moving gantry, and the LSAM 1010 was born. Earlier this year, THERMWOOD introduced the LSAM additive printer, which is a 5-foot by 10-foot by 4-foot tall machine that just has an extruder and no milling capability like the other ones. One of the special things about this is it also has a new melt core that's 30 millimeters or 100 pounds per hour of material. And finally, once we had the wider gantry, there was no problem in coming up with the LSAM 1520 and LSAM 1540. That's 15 feet wide and 20 or 40 feet long. So the THERMWOOD LSAM for large scale additive manufacturing has over 50 patents is the largest system that seems to be in production today, continually building machines every month, and has the largest market share as far as I could tell. So how do you implement additive? There are lots of ways of doing it, but one way is to work with a machine manufacturer like THERMWOOD. Another is to buy an entry-level machine. Another is to work with a value-added reseller or distributor of machinery. Or you could work with a national laboratory like Oak Ridge National Labs, but Sandia and Lawrence Livermore both have programs as well. You can work with a makerspace. This 3D printer's in the public library here in Cincinnati. Another good thing would be to work with a university. And I've worked with all these universities, but Purdue's Composite Manufacturing and Simulation Center is kind of at the lead, producing large-scale parts and testing materials. And they are a partner in IACMI, as well as the University of Dayton Research Institute, UDRI. You can work with a service bureau. That's someone that understands all the different parts of additive manufacturing, including design for additive and post-processing, and has the expertise to get you off and running right away. But my favorite one, I'm a little biased, is to hire a consultant if you have questions and want to get started. So thank you for your time. I'm Rick Neff. Here's my contact information. And I will also put it in the chat if you'd like to get a hold of me and ask questions later. I think I've used too much of your time to run through too many questions now. So I'm going to turn it over to Dale.
Thanks, Rick. I don't see any questions in the chat or in the Q&A at the moment, and we are running long on time. I do want to apologize that it doesn't appear that we're going to have Vern Benson today. I know some of you certainly tuned in for that. We will something that's probably come up, and Vern didn't log on, so we're going to go pivot straight to Professor Penumadu, and we will work to get Vern Benson with us on September 14th on our next webinar. So Dayakar, let you go into mode and start your presentation.
Thanks, Dale. Yeah, I'm going to share today with you some aspects of sensing technologies for composite materials, especially for joining as well as in situ monitoring. I appreciate the opportunity that Dale has provided to share some of this work with you. So we will provide an example application that involves composite bridge deck technology that was instrumented with both fiber optics and some wireless technology that was developed at the University of Tennessee, Knoxville. And we'll go through some example inferences from it. But we all know that we are going through the most active period now of trying to pass an infrastructure bill that resonates closely with a lot of us. And we are destined to having lots of problems with both the above ground and underground infrastructure. I think bridges are the ones that most of us see and feel the pain when you get stuck on traffic. But equally important is there's a lot of infrastructure underground, like water and sewer lines, and all of these are really in a really bad shape. So there's going to be a lot of opportunities for composite materials, and I hope IACMI would help all of its membership to explore those opportunities here. In this example slides, I want to share with you some of the work Strongwell Corporation is leading the nation in this space, especially for bridge infrastructure. On the left top, you see here, those of you who have visited University of Tennessee, walked on this bridge that connects essentially the civil engineering building here to the essentially the College of Engineering space on the hill. And this is a fiber reinforced polymer bridge. I was actually had the pleasure of overseeing this project when I was serving as a department head. And this entire bridge was put together in one afternoon, just to give you a sense of timeline. So that's the power of our prefabricated composite elements coming together and only needing fairly lightweight lifting equipment to put things in place. This involved a beam type element that is shown here. This is called an extern. It's a 3 foot wide by 1.5 foot deep. So you can get to fairly realistic structures with the pultrusion based manufacturing technologies that are using continuous fiber. So it has a fairly very good performance in terms of axial and flexural and shear capacities. They also have products such as this, where you could go in after the fact and strengthen on the tension side of this flexural deck system to overcome corrosion issues that often happen with the steel reinforcement, which is usually accounting for the tension side of the infrastructure for concrete type material systems. Here is another example of a pultruded bridge system that's been operational in Covington. So I think the message here is this is nothing new. Companies like Strongwell have done this for a number of years, but with all the new materials that we have access to now and rapid manufacturing methods, I think it's right time for IACMI and other composite manufacturers to take lead in exploring the integration of these materials. In this presentation, I was going to just share with you real quick a very exciting project that was recently completed under the leadership of a composite applications group that's based in Tennessee with a consortium of members that was led by IACMI. And this bridge was placed in a rural area that's called Morgan County. And it employed a bridge deck technology, which had glass fiber reinforced polymer-based composites in a sandwich structure configuration. It was fabricated in 2 halves and joined together with a structural adhesive epoxy, and that makes the load-carrying elements. As you know, bridge decks are the most prone to damage. And you also need to make sure you have a riding surface on it. So they're extremely difficult structural elements to design. And we already have, through this structural composites and composite application group coalition, a 100-year design life approved system that we were assessing for performance, if you will, using this bridge demonstration project. The key attributes that most of us know with fiber reinforced polymers is, corrosion, intensive areas. Obviously, they have a lot of potential for application. Much of these material systems are prefabricated, and of course, the extremely lightweight design with sandwich structure configuration, makes us employ very, very small lifting type equipment in the field, and throughput would be very, very high compared to the traditional civil engineering materials like steel and concrete. So what we wanted to showcase in this project was, in addition to all the advantages of composite materials, there's always a lingering question that, how good are these going to perform in the field? Naturally, that required sensing and monitoring, and we have plans for doing that. Essentially, one of the technologies we chose to work with is fiber optic sensing. And I think most of us know that fiber optic sensing is extremely powerful from the fact that it has ability to deal with electrical interference. It's perfectly suited for very harsh environments. Obviously, bridges typically are on top of water bodies and hard to reach environments. And the other important advantage of fiber optics is the fiber optics provide as a very high sensor density. I think Rick showed in his wonderful presentation how they were using spatially resolved temperature sensing to monitor how the temperature was being varying as they were depositing material. And similar to that, in addition to temperature, for a lot of these bridge structures, we need to measure mechanical strains as well as the environmental variables like the relative humidity and displacement associated with flexure, and also some special sensing that's needed for monitoring in-plane and interlaminar shear performances. So we have very effectively utilized this sensing technology to date. A company by the name Luna, based in Blacksburg, Virginia, manufactures this technology that we have integrated into this system. So just to kind of give you a sense of how the single point versus distributed sensors work, most of us are very familiar with strain gauges. So it's basically a resistance or resistive element that becomes a part of a Wheatstone bridge. So if it's a quarter bridge strain gauge, three other strain gauges form the circuit, and the fourth one becomes the part of the Wheatstone bridge, and a change in voltage for a given excitation would then correspond to strain on that element. And they have been our workhorse for measuring strains and interpreting deformations in materials for a long time. The requirements for strain gauges are, of course, you need to be able to connect them, you need to be able to mount them, you need to be able to make sure that if you're trying to use them underwater or exposed to saltwater environment, they have to be properly protected. And you can imagine that just in this example, if I'm looking at a 15-centimeter span, we want roughly about 5 strain gauges, that installation would roughly take about 2.5 hours, and we only have strain averaged on the gauge length at these 5 locations. Now, if I were to just replace that with one fiber optic sensor, where all I have is one connectivity which sends basically a laser of a certain wavelength here, and that traverses, and then the entire measurement system is reliant on this just one end connector. We now have up to 150 strain gauge sensing points on this one fiber optic sensor, and probably the installation time is even less than 15 minutes. So naturally, anywhere we want a large number of measurement points without having to use a lot of interconnected cabling and ensuring that they can survive this harsh environments, fiber optics makes a lot of sense. There are 2 types of fiber optic sensors. The ones we just talked about is what's often abbreviated as high density fiber optic sensing. These are distributed sensing. We also have the option to look at what's called fiber Bragg gratings, where we can have predetermined locations for Bragg sensing. And where these come into play is where we want very, very high data acquisition rate. So here with these systems, we can measure spatially resolved strains up to 100 hertz over a 20-meter length of strain gauges, or equivalent to strain gauges, 20 meters of distributed fiber optic sensing. Here we can measure the same strain at a predetermined locations, and you can actually have the gratings etched as needed at given location, and they respond to as high as 5 kilohertz type applications. So for dynamic applications, you use fiber Bragg gratings. For most of the normal applications, we would be okay with high density fiber optic sensing. So I want to quickly introduce to you the 2 applications. This technology we have developed essentially to monitor pressure vessels. This was a project that was led by Steelhead Composites in collaborations with Teijin and University of Tennessee and Oak Ridge National Labs, where we designed a 10,000 PSI pressure vessel, which used essentially a tow reg based carbon fiber. So we were, for this application, avoiding wet filament winding, and we instrumented these fiber optic sensors at the interface between the metal liner. In this case, it turned out to be an aluminum 6061 liner, on top of which this carbon fiber tow rig was wrapped, and we were able to monitor the strains at various locations through the thickness along the entire length of these fiber optic sensors. And what you see very nicely here is, this is something you miss if you were to use traditional foil gauge sensors or strain gauges, because in between these, adjoining toe pegs, if you will, or infused wet toe pegs for wet filament winding process, there is strain concentrations in the resin-rich region. And as you are load testing this to burst capacity, you get very, very high strain localizations that we were able to capture with this technology, which has never been done before. And this is an important aspect to consider, because especially with fatigue, so if we have 10 or 30,000 cycles of fill and unfill type fatigue loading, these spikes in strain corresponding to stress spikes could actually reduce the fatigue life of the tanks much more than what you would do if you just basically design based on fatigue tests, assuming the strains and corresponding stresses that are averaged over a foil region, which could miss all these singularities, if you will. This is an example of average strains compared to mechanical versus fiber optic strain. Again, this was carried up to 3,000 PSI. This happened to be for a CNG tank, and a very, very good match. So certainly you get similar information as traditional gauges, but fiber optic gives you this other additional flexibility. We also came up with this custom technology where wirelessly we send pressure that is being inside the tank, and additional variables like relative humidity and also acceleration sensing on it. So the idea here would be, if this tank is being servicing out in the field and it's subjected to some kind of accidental impact, whether it's dropped or during a crash, we have wireless sensing module custom developed for this pressure vessel that will monitor essentially the deceleration or acceleration values in multiple directions, temperature and humidity, in addition to on-demand sensing we can do for getting spatially resolved fiber optic sensors. So just as a quick drop, I'll go through some example slides for the bridge application. Here is some of our University of Tennessee research members. We decided to apply sensing for panels that were already cured. This was intentional to demonstrate that we can certainly embed sensors while the composites are being cured, if it's a thermoset, or joined if it's a thermoplastic, but we can also place the sensors after the fact. So essentially, use some kind of sanding to remove the surface oil and contaminants, and then lay down the fiber and use a high temperature epoxy to bond them. So you could see that wherever the fiber is, you measure the strain in that direction. And we have certain IP here where we can measure complete strain tensor with certain configuration of putting these sensors in composite panels. Then these two decks are glued together with a structural adhesive. So always the challenge with joining, as we know, is that the variables in the joining in the field situation is very different from the lab. So the exactly precisely knowing how good the adhesive is bonded, we can now tell with a technology called smart joint, where we embed this fiber optic inside the adhesive. And this is kind of a design concept that was developed by Structural Composites. They're based in Melbourne, Florida. Much of the original design and manufacturing was led by Dr. Reichard and Mr. Scott Lewitt, and Peter Hedger are the kind of lead folks to come up with this technology that we were demonstrating at Morgan County. And this is kind of a rendering that shows you where we put down the sensors. So we had some fiber Bragg gratings. This is for monitoring strains if vehicles are coming and suddenly stop. So we need to understand the mobilized strains, if you will, due to braking, and how good is the riding surface bonded to the structurally critical bridge deck panels. Then we have high density fiber optic sensing below for spatially resolved strain. And we also have smart joints for joining materials between the decks and the supporting beam elements. So we also did a lot of proof of concept tests before we actually moved these bridge deck panels to the site. We used whatever we could. This happened to be the high bay area of Morgan County Highway Department. And you could see that the riding surface, which has a co-cure material system with the vinyl ester based composite at the base and a riding surface with stone integrated in it. And so it is very critical to make sure that this riding surface doesn't shear off. So a lot of this development was detailed as a part of the project. And if you were to see a rendering of this, you can kind of see in 3 dimensions where we laid out the various types of sensors and load points, if you will. And this is the kind of data you end up getting. So for example, if we had unsupported deck except at the edges, so we have a nice point load system. And if you just focus here on the A to B panel width, roughly this is about 6 meters spacing. We got hundreds of strain gauge sensors from that one fiber optic continuous sensor. And you can see very beautifully that on compression and tension side, you have expected linear strain with a maximum strain corresponding to the peak bending moment at the load point. And these are other locations and orientations that I won't have time to go into, but this is, for example, 2,200 pound point load on it. And if you double that, then we have double that strain. So the beauty of this now is we can now assess the operating bridge and bridge deck system. So many of you know that a lot of our abilities in structural design and analysis with composite materials, for that matter, for steel and concrete too, is modeling joining is very, very difficult in finite element method. And so we end up designing these structures for much, much higher factors of safety than necessary. But by integrating sensing technology like this, you can actually measure and monitor the actually mobilized strains, which will be very, very small in the real world. And that way you could also save a lot of money in the designing of that system. I'd already talked to you about joining. In this case, we have this bridge composite deck joined to support steel structure. And then we have this adhesive, and then we have our smart joint monitoring the interface. I'm going to give you an example of how the smart joint works here. All of us know that the greatest challenge with composite materials is, of course, for any materials, is joining. So for welding or for aluminum and steel, even till today, everything happens in a weld. We don't really worry about the base material because that's where all of the problems are. The same way for composites, whether it's carbon to carbon or carbon to glass or carbon to metal, because of the differences in coefficient of thermal expansion and other variables, you have this mismatch of CT often leads to very, very large residual stresses and strains in the joint. Here I'm showing you an aluminum joint with a carbon fiber sheet molding compound. And because carbon fibers CTE is much lower than aluminum, if you don't accommodate for that CTE mismatch in the adhesive, then you end up with problems like this. So what we can actually do is now we embed a smart joint with this fiber optic and actually monitor what happens to this material system, this joint, as it goes through, for example, a paint process, E-coat process in this case. And as it goes through the initial temperature ramp and the subsequent temperature ramps, and as it goes through cooling and reheating, eventually at the end of all of that cycling, we can actually continuously monitor as a function of location how much is the residual strain. And then by using suitable rheological performance of the adhesives, we can minimize the logged in residual stresses. So that's the same technology we've used to now monitor this composite bridge to the beam supports. Beam supports happen to be made out of steel. This is a polymer-based fiber reinforced composite bridge deck. Obviously, there's going to be CTE mismatches. So having this ability to monitor would be very important. In addition, we have temperatures being monitored at several locations of this bridge deck, both spatially as well as through thickness. We're monitoring some deflection. And all of this data of relative humidity, temperature, strains, displacements are being transferred on the cloud using some extremely low power wireless technology that our group had developed under the guidance of one of my colleagues here. And Mr. George Lagos is the person who led that project. So now we document continuously the data on the web and on cloud, we're storing this, and of course will be used to assess the performance of this bridge deck. Now, naturally, anytime we use new technology, we have to demonstrate that it seems to work like it's expected. So here is the strains as I showed you for an example loading, and we did find some finite element calculations and compared with what we measured, and it's quite good. But of course, in addition, we know what the real mobilized strains are. I think some of you know John Unser very well. So he was actually quite instrumental in getting this project through with the collaborations from Morgan County and a lot of people from my group, a lot of students from UT and postdocs who helped it. So we actually have, as a part of our data collection, a very high resolution video that looks at this completed composite bridge deck. We're continuously monitoring displacements. We have accelerometers that can trigger after it reaches a certain threshold of acceleration values. So if there is any dynamic event like a car crashing into the side bumpers, or if there's a wreck or something like that, we can immediately capture a lot of the data at a high frequency based on those triggers from accelerometers, and also know exactly how much damage it could have been subjected to. We also came up with a very interesting technology using a magnetometer that's underneath this composite panel that can actually count the number of vehicles that are going over it. And we're also monitoring spatially resolved temperatures. So I wanted to say there was a whole big team that was led by IACMI for this demonstration project. They're all listed here. But the two key teams that I want to especially acknowledge is the Composite Applications Group, Mr. Jeff McKay, and certainly IACMI with John Unser and other leadership team that supported this. And we also would like to acknowledge the support of Mr. Jeff Cornett for a RevV program that's helping us to continue to monitor this data. And hopefully we can share this in the future of how well the composite bridge deck is performing. And we're very thankful for the team at UT Knoxville, including our chancellor, who came to support us during the ribbon cutting ceremony. And with that, I'm going to give the stage back to Dale. Thank you.
Thanks, Dayakar. So we have a question from one of the attendees that, and maybe they've since received an answer, but I'll go ahead and ask it, is how do you remedy the occurrence of the strain once you've measured it?
I mean, if it is, for example, an interface between different dissimilar elements like the bridge deck and the beam girders, then we'll have to go and accommodate for the residual strain development type strategies. But really, rest of it is, there's not a whole lot we can do. We're just going to be monitoring to see how well each element is working on its own and interacting with the environment.
Okay, great. Okay, yeah, there was a question that somebody went back to Rick. Rick answered that live in the text. So Jonathan, you can get your answer there. One thing I want to share something real quick with respect to the bridge is that is this picture.
Yes.
Yeah. So this is the bridge, and this was last week. So it was a logging truck trailer hauling a logging truck. And apparently when that thing went over the bridge, it set a flag up, and, you know, obviously there was some minimum threshold that alerted you live time that something heavy was going over that bridge. Yeah, I'm sure it's well below any danger point, but it would certainly caught the attention of folks.
That's correct. Yeah. And I think that's the beauty of actually having continued documentation of what's actually going on the bridge with the camera and also the sensors, because the coupling of that gives us that flexibility, you know, that obviously this is in a rural area, and having that ability of cloud-based decision making to help DOTs in the future would be very, very attractive.
Yeah. So, all right. Think we're all done with no other questions that are out there, and we are at the top of the hour. Again, I apologize that Vern Benson wasn't able to join us today. We'll run that to ground, and we will try to get Vern back at a later meeting. But we appreciate Rick Neff and Professor Penumadu for their excellent presentations, and I thank all of you again for your attendance at this Innovation Insights webinar. Have a great rest of your week, and we'll see you soon.
Thank you.
Thanks, Dale. Thanks, Dayakar.